Hello, welcome back. So we'll continue with our lectures. Essentially, just now I had problems with my storage of the recording, so I will now sort of continue from there. Let me open the whiteboard. Okay, as we wait, let's just mention back what we did just now was to look at the case of the conditions for chemical equilibrium when there's a chemical reaction. So we look at the case of, say, what's the reaction that we're looking at was, yeah, just to recall back, sorry, C plus D atoms interacting, and then it becomes a CD molecule. So an example would be something like your plasma thing. You again revisit. Sorry, this is positron. I mean electron. So combining with a proton to form hydrogen atom. So that's an example. One of the conditions that we had was to make sure that the chemical potential for the electrons, for example, must be together with the chemical potential for the proton. This has to be the same as the chemical potential for the hydrogen atom. Okay, so generally this would essentially to look at my notes. This depends. So this is the condition for a chemical equilibrium. And generally, we might have some, excuse me, general reaction. Then what's needed in that particular case is that the sum of this, say, reactants with the sum of the products. What is the, yeah. So this is the reactants, for example. This is a product. So the sum over all the chemical potential of the reactants, and this one is essentially the stoichiometric constants that appear inside your reaction equation. So considering that, for example, then multiply with the chemical potential, sum it up, that might be the same as the case for the products. Okay, so so that's the general case. Now what we want to treat another type of possibility is the fact that there may be no conservation law for the number of particles. We'll give particular examples after it. So in this particular case, what happens is that, okay, let's consider like system A, system B again. So the change in the number of particles in system A is going to be independent of the change of number of particles in system B. So in other words, what does that mean? That means you take dNA over dNB. Since they are independent of each other, that has to be equal to 0. So now what happens is that, remember how we get the chemical equilibrium condition is through the change in entropy. So here what we're going to do, the change of entropy will involve the partial derivatives of the entropy with respect to the number of particles. So let's look at this. For example, the partial derivative of entropy with respect to the number of particles of type A, and this has to be equal to 0 for the case of equilibrium. So this equilibrium condition. And one writes this, remember this is the total entropy, so one has to break it up into parts of the entropy. So this will be entropy for system A, and then this has to be added with the entropy of system B, the derivatives. But remember over here, dNB, the derivative is with respect to NB here, so we need to do some kind of chain rule there in order to get your partial derivative of the total entropy with respect to NA. But then this is equal to 0 because they are independent of each other. Okay. So in other words, what we're gonna have in this particular case is that your partial SA, partial NA, which is related to the chemical potential of particle A divided by the temperature, of course, then this has to be equal to 0. Okay? This is 0, and then this implies that has to be equal to 0 for the equilibrium condition. So, so this is the case where particles of type A might not be conserved in a particular situation. So when is it? What are the possible examples in this particular case? Well, photons. The number of photons might be, it's not conserved, because why? One can essentially absorb photons and destroy it. Absorb photons and destroy it. Okay. So the number of photons might not be conserved in a particular situation. So generally, any particle that, or maybe I should say whose number is not conserved, then its chemical potential is 0. So, okay, let's try to, this is page 2, page 3, okay. So, now let's try to see a little bit more with respect to this equilibrium thing. So how one actually approaches equilibrium. to chemical equilibrium. Well, let's recall what we know about the case of thermal equilibrium. Recall thermal equilibrium when it's achieved when a hotter body hotter body releases energy to the colder body. So in other words, the hotter body is, say, TH. This is bigger than TC. And the process is that when they are in equilibrium, they will come equilibrium to the same temperature. Now, what about the case of this chemical potential thing? So, what if a system has chemical potential bigger than another what you call chemical potential? Let me just check. Okay, still recording. So so consider the following. So again, we look at entropy and the rate of change of entropy. And we can rewrite this in terms of, say, again, system A, system B thing. So D and A dt. So remember, previously we had ds, okay, and then we bring out d and a. Now you just take the time derivative of that. So this becomes partial as a, partial NA, and then partial as B, partial NB. The minus sign, remember, is because of the essentially this condition that we had earlier. Okay. So, and again, the thing, the curly bracket is related to the chemical potential. So what do we have over here? So we have using the minus sign in the definition, so we need to bring it out. D and A dt, and this will be mu A over T minus mu B over T. Okay, and as I said, if it reaches equilibrium, then the entropy is maximum, and then the first order derivative of the entropy is going to be equal to 0. So what does that mean? Well, if mu A is greater than mu B, so this is going to be positive, and over here you have a negative outside there, then okay, we are not talking about the equilibrium in this particular case, so I'm going to remove that. So we are looking at the general case before reaching equilibrium. And what happens in this particular case, you know that entropy is always increasing. So we need this to be positive. So if this is positive, then this has to be negative to cancel out the negative outside. In other words, then dNA dt has to be what you call less than 0. Okay. So in other words, when a particle of type A is having a bigger chemical potential than particle of type A loses the particle, loses its number. Okay. So this is in terms of the type A and type B. Just now we have to look at the case again for the reaction case. So this is type where you have type A, type B case, and then we consider the case of the reaction one, which is a C plus D reacting to form CD. So what would actually happen in this particular case? Oops, not sure why it does that. Okay. So in this particular case, then again you use the rate of entropy change, and then we use NC as the factor that we bring out from the partial derivatives here. So here, let me just write it out in full. dsc dnc plus dsd dnd, and then minus dscd dncd. Okay. These are the same equation that we had earlier. It's just instead of just the differential there, you have your time derivative instead. And again, we relate this to the chemical potential. So this is mu C plus mu D minus mu CD over T. And because this is not the equilibrium condition, if it's equilibrium condition, then this will be equal to 0. But now you require that entropy is always increasing, then you need that. So in other words, what happens in this particular case, if say the addition of this chemical potential of the C and D atoms or particles is greater than mu CD. So in other words, this has to be positive, then this has to be negative. Okay, so that what tells us D and C, dt is less than 0, and the same happens for D and D, dt less than 0. So in other words, C and D particles will decrease. CD molecules will increase. Okay, so let me move on to a different topic now, essentially how one could actually measure chemical potential. Let me start with a fresh screen. So over here, what we have is essentially we are going to claim, so measuring chemical potential so we're going to claim that that can be done through measuring the Gibbs free energy, measuring Gibbs free energy. I will explain in a minute how this can be done. So let's recall what Gibbs free energy. Gibbs free energy is given by symbol G, which is written in terms of the enthalpy in this way, or in terms of the internal energy, the average internal energy in this particular case, because the energy can change, okay, plus PV minus TS. Now, point is over here, if we allow number of particles to change, consequence there, that means your internal energy also changes. So one looks at, say, your internal energy. So we take the differential there, and you can check that this is equals to TdS minus PdV. And this comes from the case, no, we have treated this before, but now we have to add this part, okay, where you include the change in the number of particles. So this is sometimes called chemical work, and this is essentially your mechanical work. And this one is related to heat. Okay, so I hope you can still remember those. So now what we're going to do is to put this inside your Gibbs free energy. So the Gibbs free energy will be the following. So we take differential of G, change in Gibbs, dg equals to, so we're going to do this definition here, or maybe I'll start from scratch. So dt is going to be equals to du plus dpv minus dts. Okay, and then du is given over here, so we plug that in, tds minus pdv plus mu dn, and then you minus the terms over here is, here we have vdp plus, minus pdv, and so this is a plus, this is a minus. So here is minus TdS minus SDT. So you can see that this cancels out, and essentially what we have is the following, mu dn plus V dP minus S dt. Now, we are interested in the case where we are looking for what you call things going to a chemical equilibrium, meaning the other cases where like the mechanical equilibrium is already achieved. So one would expect that in this particular case is the case for constant pressure and constant temperature. Okay, so this is with respect to mechanical equilibrium, and this is with respect to thermal equilibrium. So that has to be equal to 0. So in this particular case, we are only interested in the fact that for chemical equilibrium, okay, maybe I'll write this down first. So you have the G N partial, okay, equals to the chemical potential. And this has to be done at what? At constant temperature and pressure. Okay? Constant temperature, constant pressure. So in other words, what we have over here is to say that if you do that, then one can identify that this partial derivative of dg dn is going to be proportional to the Gibbs free energy itself divided by n. Okay? But you know that dg dn is equal to the chemical potential, so in other words, that tells us chemical potential is given by Gibbs. Sorry, this is not 0 there. G here over n. Okay. So in other words, if one is able to measure the Gibbs free energy, then one can actually measure your chemical potential. All right. So I think I will stop there for now, and we'll continue later on, and hopefully, I get enough time to record all the things I want to say for this chapter. So I'll stop there.